everybody, and thanks guys for the invitation. I'm going to try to be a bit more technical than Stefano, basically. It's going to be a practical example of what we've been achieving in the last few years, implementing mainly automation in our routine labs, Dioxin and PCB analysis, mainly in food and feed, but also a little bit in human for some biomonitoring campaigns. I want to, of course, take the opportunity to thank my co-author, George and Gauthier are really taking care of the routine lab in Liege, and Professor Depot is basically the one that originated the Dioxin activity in Liege like 15, 20 years ago. So, yeah, that's the wrong button. This is what the situation today in the routine lab in Liege at CART. So CART is the Center for Analytical Research and Technology in Liege. When we receive sample in the routine scheme, it will fall in one of those boxes, if I can say so, where if it's just fat or fatty matrices that don't require extraction, we will be able to give back the data to the customer or to the government the day after. So we call that the day plus one approach, basically. So it's a bit more than 24 hours to be able to, between the time we receive the sample, we enter the sample in the system, and the time we are able to send electronic report to the customer. So from what we've been used to deal with in terms of timing, it's kind of a nice improvement for the last few years. If we have to go through extraction, for example, for some of the feed or feed ingredients that we have to process, it's taking a little bit more time because we have to go for, to dry the stuff because we receive sometimes very strange feed or feed ingredients. You have to dry those overnight, basically, and then you have to extract them using PAE, for example. So it takes a bit more time. And then once you get the extract, you can go back to the scheme of the fatty matrices. And if it's a matrix that we don't know, if somebody knocks to the door in the lab, and sometimes it happens, sometimes we receive some beer or some chocolate in Belgium, it's important to check that also. And we say, okay, then we need 5 days. Basically, we need 1 week for the unknown matrices, because sometimes we have to develop or to adjust the methodology that we're using. So I'm just going to briefly describe those different approaches. So the day plus one, so the strategy that we use to be able to get back to the customer after 1 day, it's a bit more than 24 hours actually, concern mainly the fat, the vegetable oils or the animal type fat. So that when we receive those fat, we do not extract those. We just process them directly versus sulfuric acid impregnated silica, for example, or we can directly process them without extracting them. So we are importing a gram of fat basically because it's literally pure fat then. Depending on the fat, because it's different type of fat which are under different legislation in terms of maximum residue level. This is the sample size that we usually work with up to 7, even 8 grams sometimes, because some of the levels are lower, especially in pork fat, which is good for us, but us as a human being, but bad for the analytical chemist basically. So it's sometimes challenging to be able to process that big amount of fat. If we, for example, look to fish oils, we normally use much less fat because it's lower levels. Plus, for those of you that are processing this type of samples, you know that fish oils are much more challenging to process than animal fat. The other animal fat, I should say, because the composition of the fat is a bit different. For the vegetable oils, we have to increase the sample size because the levels are most often very low. So this is how it's happening in the lab. So if you would come to the lab to say, okay, I've got a fat sample to be analyzed, so you have to be in the lab before 9 a.m. on day 1. If you come after 9, you're losing 1 day, basically. So if you want to enter the day processing, you have to come before 9. So we're just going to receive the sample, it's ISO17025 environment. So we're going to receive the sample, put the sample in the system. We're still not using barcodes, but we're probably going to move to that quite soon to improve or increase the speed with which we can enter the sample in the system, basically. So we just, receiving the sample, we just do inspection. In analytical chemistry, the most important step is the sampling. So we have no control on the sampling in our lab. So the only thing we can do is to check for the integrity of the sample. So if we see that the sample has been leaking and things like this, we just refuse the sample. But we have no idea about the sampling step. That's not under our control. So, it just takes like half an hour and then the sample directly enters the the analytical process, basically. So we just take the weight that we need for the sample, we do some dilution in hexane, for example. We do the spike because, of course, the legislation wants us to do isotope dilution using C30 labels, standard, etc., etc. And that's really the first step of the procedure, where we end up in, let's say, 50 milliliter of a solution containing the few grams of fat that we have to process. So then the next step would be to get rid of most of the fat. So different approaches depending on the matrices. We're using the power prep system for the automated sample preparation and fractionation. But sometimes if it's very bad sample or big amount of fat, instead of using directly the high capacity disposable silica column on the automated system, to kind of preserve the system from fat contamination, we do a quick and dirty manual glass type column for acidic silica. This is disposable glass column, so we just pack them very quickly, we just pour the sample to the column, so a lot of lipids are degraded, and then we move to the pore prep. So in that way, we are keeping the pore prep on the safe side, especially if you want to do human biomonitoring campaign, where the quantity of lipids are much lower. We try to keep away from loading too much fat in the system. But basically, if you take a full multi-layer or a full acidic silica column, disposable column for the pore prep system, you can go up, depending on the fat, to 8 grams. So in practice, it works as well. So then, of course, because of this liquid chromatography step, we increase the volume of the sample, and we don't want to load, let's say, 120 mils on the pore prep system. So we do a quick concentration step using very simple rotary evaporation devices. So let's say we go from 200 milliliters to, we reduce by a factor of 10, basically. So we have this 20 milliliter of extract, which is from, let's say, 8 grams of fat, which now contain much, much less fat. So this goes to the direct classical sample procedure for the cleanup procedure on the pore prep system. So this is, most of you have seen those systems or even using those systems. So we use actually 2 sets of those systems in parallel in routine. So we've got 10 lines, and normally we have 8 unknown samples, 1 QC, 1 blank. So that's what we call a series of samples. So we're going to just load the sample on those disposable columns. The remaining lipids are going to be degraded. The fractionation will take place on the basic alumina and the carbon column. So we're going to end up with 2 fractions. One fraction basically for the PCBs, the Dioxin-like PCBs and the PCBs, or the mono PCBs, and another one with the other PCBs and the brominated flame retardant if we have to look at those flame retardants. Although we have to keep in mind that it's much more challenging to do the BFRs because of the lower levels and potential contamination levels in the lab. So that's something to take care of. So we end up, after let's say 75 minutes, the run is over. So if you run the 2 instruments in parallel after 1 hour and 15 minutes, you've got your PCB and dioxin fractions that you have to evaporate, basically. So this is just a scheme for those of you that don't know the system. The pore prep system is a very simple system, and it became, over the years, it became a very robust system. So the last version we bought was quite some years ago already, and it's just a system that utilizes valves. So it's a low pressure system. So it's, let's say, 20-25 psi inside that system. So it's a low pressure liquid chromatography system where you have the opportunity to load your sample and get your sample to go through different disposable columns, which are packed with either multi-layer acidic, basic, or neutral silica, basic alumina, or carbon adsorbent or sealite. So you basically get the fat degradation. In this configuration, there is a big column to take care of lots of lipids. Then for the fat degradation, you load the alumina column, so some of the degradation product can go to waste at that time, and then you shift your solvent to a mixture of 50-50 hexane, dichloromethane, and then you just push out the compounds of interest that you will basically partly trap on the carbon column. The planar compounds will be trapped, the non-planar compounds will go through, and then you start to do the collection of the non-planar species, basically. Then you do a backflush of this small carbon column, and you will collect the planar species, so the Liege PCBs, the coplanar PCBs, and the fluorescents. So you end up in different fractions, basically 2 fractions, the planar versus the non-planar compounds. And in the new configuration of those systems, you can directly collect in collection tubes, which are inserted in the evaporation device. So as soon as you are collecting, after a few minutes have been collected, you can already switch on the evaporation device to save a bit of time. You don't have to wait for the complete elution to be over to start the evaporation. So this is where, again, you save a few minutes And by saving a few minutes here and there, this is how you can end up doing it in one day. So this rapid pub system basically stops with a sensor, so it will basically stop at the level that you decide, and then you will be able to take it to the next step, basically. This is just one of the examples of the program. There is a nice software with the FMS system where you can visualize the step of your program, but I'm still from the old school where I used to write this program in just a spreadsheet, which for me it's easier to see, although I can understand that for those that are not used to it might be strange, but you're basically coding the different steps and basically what you want to do. So you're going to fill the tubings, you're going to be conditioning the solvent, you're going to be loading your sample, you're going to be changing the solvent, you're going to be flushing, back flushing, etc., etc. So this is just a quite simple program. This is about 75 minutes. We've been quite simplifying this program because it used to be a bit longer, so we've been cutting here and there different step by optimization. So this has been validated, and actually the last version of the program is even shorter than this. We removed a couple of steps again. Of course, you don't want to have any cross-contamination because you're using the same automation system, so automated system. So from my first series of sample, and I'm going to shoot my second series of sample of the day, I want to be sure that the system has been properly decontaminated, if contaminated. So, of course, what we avoid to do is to do a fly ash in the morning and a human serum in the afternoon. If you do that, you're going to be screwed. If you do that on the high-risk aspect, you're going to be screwed as well. The ion source, the ejector, everything will be contaminated. So we have to, I would say, keep one system for one type of matrix or one type of level. Food, human is compatible, but don't put sediment or fly ashes on the same day. So this is just the quick, this is 15 minutes, the quick washing program. This is just passing some solvent through different lines. So that's quite easy to do. So you just have to push the button on the computer and that will do the job. So this is how it looks like at the end of the collection. So as I said, 2 fractions for each sample. So if I had 10 samples, I would end up with 20 fractions. And this is not inside the evaporator because if this is inside, you don't see anything. So we remove the tube from outside. So this is the volume of the collection. So one of the fractions for the back flush for the planar species is about 80 mils. We scale it down to 70 mils actually quite lately. And the non-planar fraction is about 100 mils of hexane dichloride. Of course, this is where we should still do efforts to try to reduce the volume of solvent. Obviously, everybody agrees on that, but we're still working on that. But we've seen that if we just use 50 mils instead of 100, we kill the recoveries. So there is no miracle, there is a compromise to find. But we're still working on this volume reduction. So this is the way we used to evaporate the sample. This is classical turbo systems where you just use also a sensor to sense the end of the evaporation. But in that system, we had to wait until the evaporation was finished to move the tube from the FMS system to the evaporator. So now the evaporator is just sitting, the power pump is just sitting under the power pump system. We don't see anything, but believe me, there is like 300 microliter of solvent down there. So this is when the sensor stops. So those 300 microliter have to be further reduced to, let's say, 10 microliter before GCMS injection. Unless you want to do large volume injection. I know Wim is there today, maybe we'll talk a little bit about that, but at Liege they've been developing a large volume injection procedure which works very well. So that's probably the next step in the optimization there. So we used to have a manual transfer of what is basically like what is there. We just take a plaster pipette, we just move it to a GC vial. So that's also used to take some time. So now with the last version, this is where we finalize evaporation from let's say 300 to 500 microliter. But then we end up in this, let's say 5 to 10 microliter. So it's a big concentration factor between the starting point where we had 8 grams of fat down to, let's say, 5 microliter containing the clean extract. So this is 5 microliter, so it's not much. So you can inject it once or twice on the GCMS because we inject 2 microliters. So if it fails after 2 injections, you have to redo everything. What we use now is, again, to save the time that you had to take the plaster pipette and transfer the sample and potentially have a contact between the sample and the lab environment, and you can always use a drop, and when you have 5 microliter, if you use a drop, you kill the recovery by a factor of 60%. Now there is this very nice type of tubes, which basically at the end you have the GC vial, which is crude. So once the evaporation is down to, let's say, 300 microliter, the sensor will stop. So you've been starting the evaporation during the collection, the sensor will stop, then you unscrew the GC vial, you just move it to the next final evaporation step, down to, let's say, 5 microliter, or you do after injection, and you save a little bit of time. And maybe the most important point is that, as I said, the sample is not exposed to the lab environment, to the dust, for example. For the brominated flame retardant, it's quite important. So that's one of the last improvements that we enjoyed, basically. So by 4 p.m. the same day, this is one serial sample. There is 20 GC vials, so there is 20 extracts, so it's 10 samples, 8 unknown, 1 blind, 1 QC, and there is every time like a dioxin fraction and a PCB fraction. So this goes to the rack, and that goes to the GC mass spec person, which has been optimizing the GCMS for the afternoon. So by 4 p.m. it's ready to get the sample, put them on the other sample, and switch on, push the button, and the injection will take place overnight. It's 2 different injections still. It's 1 PCB injection and 1 dioxin injection. We could, do 1 injection on, for example, TOF-MS, for example, but it's still not accepted. So we still also work on that. We just use classical iris mass spec. By the next day, so that's day 2, 9 a.m., everything has been injected. Luckily, everything went fine, so we just recovered the data. So it's a lot of automation, a lot of macros that have been created. We use the XML format to basically report, so we do all the QA/QC check on the next morning. And the deal, basically, with the customer is to be able to get back to be able to send back the data before 4 p.m. on day 2. Most of the time, we are able to send the data before lunchtime, but we just take a little buffer for a few hours in case something goes wrong. Because if we have to redo a quick re-injection in the morning, we can. If we see that on the 20 sample 18 has failed for a reason, we just take it in the morning, reshoot it, and then we have still a couple of hours to send it to the customer. One thing also, we for a few, probably like 4 or 5 years now, we are using, let's say, 2 shifts in the lab. So the first group of technicians will arrive in the lab on 6 a.m. and will end the day at 2 p.m. And the second group of technicians, when I say group, it's just 1 or 2 persons, it's not a big lab. But at least there is some overlap, so some persons are able to, from 6 to 9, so before the deadline to receive a sample from the customer, we already have 3 hours to take care of some stuff in the lab. So, and then the second group of people will end at 5 p.m. So that helps a lot. It looks okay, it doesn't make any difference to have like 3 hours, but virtually we have a 1 day is 11 hours of work. So that makes a difference versus an 8-hour work. So sometimes it's difficult to convince people, of course, you're going to come and start at 6 a.m., but most of the technicians have young kids, so they sometimes are very interested to start early to go back home at 2 p.m. and take care of the kids. So that helps to convince people. So that's for the easy one, no extraction. But then if you have feed or feed ingredients, we have to do extraction. So that's a bit more complicated, so the strategy is a bit different. We will accept the sample until 3 p.m. on day 1. So after 3 p.m., that's the time we need between 3 p.m. and 5 p.m. to basically prepare the sample for overnight drying. So we're going to take the aliquot of the sample, we're going to mix it, grind it, because feed ingredient can be anything. Sometimes it's really, surprising. So we're going to, homogenize it, and then we're going to dry it overnight. So this is why it takes longer, because we just need, let's say 8 to 12 hours to dry the sample, because you have to report the dioxin levels on high weight. So you have to be sure that you have a constant weight after drying. So that takes basically the night. Then the next day the extraction can take place, so we use the PLE or ACE, that's the same type of technology. So we just have to fill the extraction cells, spike, respecting the procedure for spiking, use a defined procedure in terms of pressure and temperature for the PLE. It has been quite some report on the importance of those parameters, because if you just use, let's say, 100 degrees C instead of 130 degrees C, if you use hexane instead of hexane with a little bit of acetone or with a bit of toluene, it makes big differences. So it has been a lot of work done by different labs on that to optimize the solvent mixture. This is 1, 2, 3, 4, 5, 6 lines in parallel for the PLE. So that's the FMS system for PLE. So you can, in parallel, have the extraction going on. So for us, it was quite interesting to move from a sequential overnight type of extraction using the ACE system to move to a parallel extraction type situation, because then it can be done during the day. And in the procedure of day with 3, that's better for us to do the extraction during the day, so it's better to go parallel than in sequential basically. But that uses high pressure and solvent basically. So after the extraction, this is the scheme, so just an oven that you can pressurize, you've got a high pressure pump, you fill up the solvent, you heat under high pressure, so you can use the solvent above the boiling point, so that's why the solvent, the extraction efficiency is better. So that has been reported back in the 1980s already. So just the type of cell that I use, so no need to screw the cells. So again, you can save a few minutes not having to screw the cell, just plug in the cells, and this is leak-free, so that's kind of nice. Then after the extraction, you have also the option, when you do the extraction, to directly collect the extract from the PLE in those evaporation tubes I just showed you. But it's much more difficult because after the extraction, it's a lot of thing in the extract. So it's more difficult to evaporate that in a small GC vial than to evaporate a very clean extract after the cleanup step. So still, we use some of the rotary evaporator there. Then we have a solvent exchange, because if you've been extracting with toluene acetone, this is not compatible with the cleanup step, where you have to be in hexane media. So we just have to exchange the solvent to be able to go for the cleanup step. So then those samples are ready to join the regular procedure that I showed earlier, the day +1. So after this extraction and drying, we can reach that. So this is just why it takes a bit more time because of the extraction. Same thing, QA, QC, and then we report to the customer. That's the same thing that we just saw in a minute. And right now in the lab, as I said, it's not a big team of people. It's just we are a very little lab, basically. But having been in the direction of automation helped us a lot to basically ease the life in the lab. So right now the configuration is just a few, 3 technicians, which are full-time employees. There is just 1 analyst, which is not full-time. There is 1 engineer taking care of the reporting, basically. And there are 2 PhDs, which are just part-time, like 25% of the time in the lab. So it's not much manpower there, but still we can do quite a lot of samples. In terms of instrumentation, this is what we have today. Well, we have 1 PLE and 1 ACE, so we're still using both, and so we can do some comparison. We've got 10 lines of cleanup systems. We've got still 3 rotavalves, we've got some turbovalves, and we are shifting to the power valve where we can use the GC vials. And we have 2 high-res mass specs, so if one is down, we have a backup plan, basically. What I would say are the key aspects of this is that we've always been in close contact with the companies which are selling those automated systems. So anytime we wanted to modify something, we could easily get back to, for example, to FMS and say, listen, this is what we would like to do, could we improve this or this? And then what we were doing in research was directly transposed in routine. So that's, I believe, is a key aspect to get things modified. Tomorrow I will talk a little bit about the performance-based method, basically, that we have to use for Dioxin. And because we are kind of free of doing, I'm not going to say what we want, but you are able to modify your methods. If you are able to validate them, they will be accepted for Dioxin. So that's a very nice point for those methods. So also what we do in the lab, as I said, we receive samples until, let's say, 9 a.m. in the morning. So that will be the first series of samples that will go to the reception, if extraction, then cleanup, etc., etc. But if you take it as a first axis, basically, and then that we have second axis, we can start to shift series of samples. So it's like a multidimensionality of the sample reception, basically there. So you can start series of sample, and once the first one is done, you can start another one. So there is overlaps and shift in addition to the fact that people come at 6 a.m. or 9 a.m. So that basically make the lab to be used all day. So that's also important. This is the sample flow. Those are numbers from 2 years ago. So it's not huge. It's just classical number for such a lab. And as I said, we do mainly low-level sample. We don't do fly ashes and sediments on those in this routine lab. We have another higher level lab that take care So basically, it's like 2,000 samples a year for, let's say, 5 persons, if you take care of the full-time employment or not. So it's like 400 samples per person per year. So that would be very interesting to discuss that with other labs to see where we are allocating ourselves for that. But I believe it's not too bad as a ratio. So to conclude, what's the next step, basically, in which direction are we going? Evaporation stages. It's still the bottleneck of the procedure because we are using quite a lot of solvent, even if we are trying to reduce it. So we have to speed up evaporation procedure. Nice with the new Prof evaporator, but we need to go even further. So this FMS evaporator is definitely something that we are following closely. Keep talking with manufacturer. We are very excited about multi-dimensional GC that would allow us to do only 1 injection instead of doing 2 injections, but then you have to do high resolution. So GC, high resolution sector instrument. So we have an ongoing project with Thermo on that. So we hope we can arrive somewhere in the future. Software's improvements, better MCPs, maybe if you want to do tough MS on regular top that I use on GC, that would be nice to improve the sensitivity, of course. Finish with this, better complement between sector high-risk mass spec and tough high-risk mass spec. We'll talk about that a little bit tomorrow, but I'm convinced that next to the SIM or target analysis, we need to extend it to other compounds because they're going to be there, those fractions, but we just don't look to them, although they are also potentially toxic. So that's something that should keep our attention for the next few years. So from that, I'm going to stop here. I believe I'm